The vast interstellar empty space between the stars is often described as a silent vacuum of nothingness. We look up at the night sky and see a structured map of bright stars, each anchoring a family of planets in stable, predictable orbits. In our local domain, the solar system feels like a permanent, secure fortress, protected by the immense gravity of the sun and the shield of our outer planets. We build our cities, chart our future, and live our lives under the assumption that the planetary tracks we orbit are immutable, locked in an eternal circle of warmth and light. Historically, humanity has viewed the heavens as a perfect clockwork mechanism, operating with mathematical precision. But this planetary stability is a rare, delicate anomaly. The deep space between systems is actually a dark, cold ocean populated by millions of invisible wanderers. These are objects of immense mass, drifting through the dark void at colossal speeds without orbiting any star. Among them are rogue planets, massive worlds ejected from their birthplaces, and wandering black holes, stellar mass ghosts, traveling silently through the cosmic vacuum. They do not emit light, they do not reflect warmth, and they leave no heat signatures. They are gravity-driven torpedoes moving through the dark arms of the Milky Way, traveling for billions of years across the galaxy. If one of these massive objects were on a trajectory toward our solar system, it would not even need to collide with Earth to end our civilization. Gravity is the invisible fabric that holds our orbits together. A passing intruder would act as a tidal crowbar, warping the orbits of our planets, destabilizing our climate, and pulling our world out of the habitable zone. If you want to understand the terrifying physical limits of our cosmos and the invisible threats roaming the galaxy, subscribe to Deep Space Signal. Let's decode the universe together. The story of these dark wanderers is a reminder of our cosmic fragility. We live on borrowed time, separated from a chaotic universe by a thin veil of orbital mechanics. The distance between stars seems like an impassable barrier. But to a nomad black hole or a rogue planet moving at hundreds of kilometers per second, these gaps are easily crossed. The vast void is not empty. It is filled with these silent projectiles, moving through the darkness like ghosts, bound to no sun. Today, we run a realistic gravitational simulation, tracking what would happen if a silent massive intruder entered our local space, destabilizing the fragile gears of our solar system, and forcing us to confront the true horror of the interstellar void, where Earth could be lost forever in the dark, frozen and isolated from the rest of the cosmos. We must observe these dark wanderers with vigilance to protect our future. To understand the threat of rogue planets, we must first look at how they are born. Planetary systems are not created in perfect harmony. During the early stages of a star system, the birth of worlds is a violent game of gravitational tug-of-war. Young planets orbit in tight, unstable configurations, surrounded by leftover gas, dust, and planetary embryos. As they grow, their gravitational fields begin to interfere with one another. This is especially true during the planetary migration phase, where giant planets shift their orbits inward or outward, disrupting the stable paths of smaller worlds. When a massive gas giant, similar to Jupiter or Saturn, passes close to a smaller terrestrial planet, the exchange of orbital energy is catastrophic. The massive giant slows down slightly, while the smaller world is accelerated to extreme speeds. If this speed exceeds the escape velocity of the host star, the planet is violently ejected from its birth system. It is cast out into the interstellar medium, doomed to drift through the cold dark forever. This process of protoplanetary migration is a fundamental driver of planetary instability. When massive gas giants migrate through the disk of gas, their orbital resonance sweeps through the system, acting as a gravitational slingshot that ejects smaller planets. This means that a large fraction of the worlds formed around a young star are destined to be cast out, turning into lonely wanderers of deep space. For decades, astronomers believed these orphan planets were rare exceptions, a minor byproduct of star formation. However, modern surveys and computer simulations have shattered this assumption. Upcoming space observatories like the Nancy Grace Roman Space Telescope are designed to conduct massive surveys using gravitational microlensing. Searching for these dark targets, modern surveys suggest that there are billions, if not trillions, of rogue planets wandering through our galaxy. They may outnumber the stars in the Milky Way by a factor of 20 or more. The dark void between systems is actually teeming with these silent wanderers. They range from small, frozen rocky bodies like Mars to colossal gas giants that are many times larger than Jupiter. Without a central host star to provide warmth and light, These frozen worlds undergo a dramatic physical transformation that locks them in ice. Their surfaces lose heat quickly, dropping to temperatures near absolute zero. Their oceans freeze solid, forming miles of rock-hard ice. Eventually, even the gases in their atmospheres, like nitrogen and oxygen, condense and rain down onto the surface, freezing into sheets of solid gas. They become silent, dark projectiles traveling through the galaxy, completely invisible to the naked eye. Without a sun to guide them, they drift through the stellar neighborhoods, ready to cross the boundary of any stable star system that lies in their random path, introducing chaos to established systems. While rogue planets are cold and silent, the galaxy hides an even more dangerous wanderer: nomad black holes. These are not the supermassive monsters that sit safely at the centers of galaxies, feeding on giant gas clouds and shaping galactic structures. These are stellar mass black holes, the compact remnants of dead giants, and they are moving through the stellar catalog at incredible speeds. When a star with over 20 times the mass of our Sun reaches the end of its life, it runs out of fuel to sustain its outer layers. The iron core collapses under its own weight, causing a rebound shock wave that triggers a core collapse supernova. But this birth is often chaotic. If the resulting supernova explosion is not perfectly symmetrical due to instabilities in the collapsing core or uneven neutrino emissions, the shock waves are thrown out unevenly. This asymmetrical blast creates a powerful rebound effect known as a natal kick. The newly formed black hole is shot out of its birthplace like a projectile from a cannon, traveling at hundreds of kilometers per second. Free from the gravitational lock of its parent cluster, the black hole wanders the galaxy alone. During a core collapse supernova, the sudden collapse of the stellar core creates extreme physical conditions. The star's iron core collapses in less than a second, reaching densities higher than atomic nuclei, before bouncing back in a violent shockwave. If this bounce is even slightly off-center, the asymmetric energy release launches the newborn black hole out of its birth cluster at orbital escape velocities, transforming a massive stellar core into a permanent nomad. Because they do not emit any radiation, they are completely invisible. They do not have accretion disks or glowing gas clouds unless they are actively feeding on a nearby star or crossing a dense molecular cloud. Most of the time, they are simply pockets of pure gravity traveling through the dark. Astronomers estimate that there are over 100 million stellar mass black holes in the Milky Way alone. Many of these are bound to binary star systems, but millions of them are nomads, crossing the interstellar void. They roam through the same spiral arms that our solar system inhabits. If a nomad black hole were heading toward our region of space, we would have no visual warning. There is no surface to reflect light, no atmosphere to detect, and no radiation to measure. It is a ghost in the dark, detectable only by the gravitational lens it creates as it bends the light of background stars. It travels through the cold lanes of space, a silent threat that could cross our solar system boundary without a single warning, shifting the gravitational balance of our planets before we can even point our telescopes toward it. We must watch the dark spaces for warnings. If these wandering monsters are so common, why can't we see them? The answer lies in the fundamental limitations of our observation technology. Our telescopes are designed to detect light, radio waves, or infrared radiation emitted by active objects. Stars glow, nebulae shine, and active galaxies beam energy across the cosmos. But a rogue planet or a quiet black hole produces no light of its own. They are the ultimate blind spot of modern astronomy, hiding in the shadows of the interstellar void. To find these dark wanderers, scientists must rely on indirect methods that do not depend on light emission. The most successful technique is gravitational microlensing. When a dark object passes directly between Earth and a distant background star, its intense gravitational field acts as a lens. It bends and focuses the light of the background star, making it appear temporarily brighter. For a few days or weeks, the star flares in our data, revealing the mass of the invisible interloper. But microlensing requires a perfect, rare alignment of stars, separated by thousands of light years. Once the alignment passes, the dark wanderer disappears back into the blackness, its path and destination lost to us. During a microlensing event, astronomers plot the light curve, which is a graph showing the brightness of the background star over time. A normal star's light curve is a flat line, but when an invisible wanderer passes in front, the gravity bends the light paths, creating a symmetric spike. The duration and shape of this peak allow scientists to calculate the exact mass and speed of the interloper, even if it remains completely dark. This shows the power of physics. We cannot track it, calculate its trajectory, or predict where it will go next. The physical geometry of the event is a one-time occurrence. This means our solar system is vulnerable. A rogue planet or a nomad black hole could be on a trajectory toward our sun right now, and we would remain completely oblivious. It would slide through the deep space between stars, undetected by our infrared sweeps and sky surveys. Our first warning would not come from a visual image, a telescope photograph, or a sensor alarm. Instead, it would appear as a subtle mathematical anomaly in our orbital tracking models. We would notice distant comets in the Oort Cloud leaving their stable orbits and falling inward toward the sun, pushed by a gravity we cannot see. The comets would act as the early detectors, their orbits disrupted by the gravitational wake of the incoming mass long before the object itself gets close to our major planets. By the time we confirmed the intruder, the gravitational collapse of our system would already be underway, giving us little time to react, leaving humanity to face the ultimate challenge of survival. The boundary of our solar system is not a sharp edge, but a vast, spherical cloud of icy bodies known as the Oort Cloud, extending from 2,000 to over 100,000 astronomical units from the Sun. This region holds trillions of comets and frozen remnants from the birth of our system. Here, objects drift in a delicate gravitational balance, barely bound to the distant Sun. Their orbital velocities are slow, measured in meters per second, making them extremely fragile and easily disturbed by any passing galactic force. It is here, in this frozen boundary, that our simulation begins. Imagine an invisible dark mass, a rogue planet several times the mass of Earth, approaching from the deep interstellar void. It does not flash or leave a trail of fire. It is a quiet visitor, detected only by the physical disruptions it leaves in its path. As the intruder crosses into the Oort Cloud, its massive gravity acts as a gravitational plow, displacing the icy bodies. The delicate balance that has existed for billions of years is instantly broken. The comets closest to the intruder's path are violently scattered. Some are thrown outward, sent into the empty space between systems to wander forever. But millions of others suffer a different fate. Their orbital velocity is slowed down, causing them to fall inward under the pull of the sun's gravity. A massive, unprecedented rain of comets is initiated, heading directly toward the interplanetary region. In this outer boundary, cometary orbits are so large that a single orbit can take millions of years. Because the sun's gravity is so weak at these distances, the gravitational pull of a passing massive body easily overwhelms the solar attraction. The intruder acts like a massive gravitational wake, pulling comets out of their stable orbits and sending them falling toward the inner solar system, transforming a quiet region of ice into a chaotic field of falling rocks. On Earth, our automated sky surveys, such as the Vera C. Rubin Observatory, would begin detecting an anomalous spike in new cometary discoveries. In a matter of weeks, telescopes would catalog thousands of long-period comets emerging from the dark, all sharing the same general trajectory. At first, astronomers would search for a visible cause, suspecting a distant star cluster or a known asteroid belt collision. But the data would show no visible culprit. Instead, the comets would keep coming, their numbers growing daily, their eccentric orbits pointing to a single source of perturbation. This Oort breach is the first physical signal of the intruder's approach. It is the outer wall of our fortress collapsing, a silent alert that a massive gravitational wave is rolling toward the inner planets, pushing a vanguard of icy rocks ahead of it. This threat is real, silent, and extremely dangerous. As the invisible intruder travels deeper into our system, it reaches the orbits of the outer giants, Neptune and Uranus. These massive worlds, containing many times the mass of Earth, have orbited the Sun in stable, circular paths for over 4 billion years. But their orbits are held in place by the Sun's distant gravity, which is weaker at these extreme boundaries. When the intruder enters their region, the physics of three-body interactions take control. The intruder's gravity pulls on both the Sun and the planet, disrupting the delicate equilibrium. Neptune is the first giant to feel the drag. Its orbit is stretched and warped, changing from a circle into an elongated ellipse. This means that at its closest point, Neptune is pulled inward, while at its farthest point it is cast further out. Uranus quickly follows, its orbital plane tilting under the vertical pull of the intruder. The rings of Uranus wobble and deform as tidal forces stretch the planetary dust. This orbital warping is not just a cosmetic change in space maps. It has catastrophic consequences for planetary moons and stability. Triton, Neptune's largest moon, which orbits in a retrograde direction, has its orbit destabilized. The tidal friction increases, and it is either pulled inward to be ripped apart into a new ring system or thrown out of Neptune's gravitational grip entirely, becoming an independent wanderer. To model this interaction, astronomers use three-body calculations, which track the gravitational forces between the Sun, the giant planet, and the massive intruder. These mathematical models show that when the intruder's gravity matches the local orbital energy, the circular orbits of Neptune and Uranus become highly unstable. This instability breaks the orbital resonance that has kept these planets separated for billions of years, causing their paths to swing dangerously close to one another. As the orbits of Neptune and Uranus cross and shift, the two planets begin to interact directly, their gravitational fields tugging on each other in ways they never have before. On Earth, astronomers analyzing telescope data would observe a sudden, unexplained drift in the positions of the outer planets. They would fail to find them in their predicted locations, confirming the presence of a massive, invisible gravitational anomaly moving through the system. The outer giants, which have acted as the primary guardians of our solar system for billions of years, have been completely compromised. Their orbits are now chaotic, starting a domino effect that will ripple inward toward our own world. The orbital period of these giants changes, breaking the resonances that kept the outer solar system stable. The gas giants, once the reliable protectors of the inner system, are now transformed into active sources of gravitational chaos themselves, pulling other celestial bodies out of their ancient trajectories and initiating a system-wide chain reaction of disruption. The intruder now penetrates the core of the solar system, reaching the domains of Saturn and Jupiter. Here, it encounters the planetary giants that hold the ultimate gravitational authority over the inner system. Jupiter, with over 300 times the mass of Earth, acts as a planetary vacuum cleaner, its strong gravity protecting the inner rocky planets from stray comets and asteroids. But as the intruder approaches, this cosmic balance collapses. Saturn's ring system, a delicate structure of ice and dust held in place by precise orbital resonance, is the first to show visible damage. The gravity of the intruder tears the rings apart, creating massive gaps and sending ice particles flying in random directions. Saturn itself is pulled out of its stable orbit, its moon system destabilized. Next is Jupiter. The encounter between Jupiter and the intruder is a clash of giants. The gravitational interaction between these two massive bodies sends ripples through the entire system. Jupiter's orbit is shifted, causing its massive gravity field to wobble. This wobble is catastrophic for the main asteroid belt, which sits between the orbits of Mars and Jupiter. For billions of years, Jupiter's gravity kept these rocky bodies in a stable band. Now, with Jupiter displaced, the asteroid belt is completely destabilized. This gravitational disruption reaches a peak in the asteroid belt, where Jupiter's orbital shift destroys the delicate resonances that keep these space rocks in stable paths. The Kirkwood gaps, which are regions kept clear by Jupiter's gravity, are filled with scattered debris. As the asteroids collide and break apart, they are thrown into the inner solar system, creating a continuous barrage of space rocks that threatens every rocky planet in its path, ending the long era of safety. With the Kirkwood gaps destroyed, millions of asteroids are thrown out of their stable paths. As this debris cloud moves inward, it crosses the orbit of Mars and heads toward Earth. The inner planets have no gas giants to protect them, leaving their surfaces exposed to constant impacts that can vaporize atmospheres and wipe out oceans. Our automated networks would track these incoming objects, plotting their trajectories, but there would be absolutely nothing we could do to deflect them. They collide with one another, breaking into smaller fragments and scattering in all directions. A massive barrage of rocky projectiles is unleashed, heading toward the inner solar system, exposing the rocky planets to a constant rain of debris. On Earth, our sky monitoring networks would report an alarming increase in asteroid encounters. This becomes a daily hazard. The safety shield is gone, replaced by a chaotic storm that marks the path of the approaching intruder. The inner system is no longer a protected sanctuary, but a high-risk zone filled with unstable rocky fragments that threaten to collide with our planet. The intruder now crosses the orbit of Mars, entering the inner solar system. It is now close enough to interact directly with Earth. Even without a direct physical collision, the gravitational field of the incoming object acts as a giant tidal force on our planet. Gravity decreases with distance, which means the side of the Earth facing the intruder is pulled more strongly than the center of the planet, and the center is pulled more than the far side. This differential pull stretches the Earth like a rubber ball, wringing the planet from the inside out. The oceans are the first to react. The gravitational pull creates massive, permanent tidal bulges. Water is pulled away from the poles and concentrated in giant swells that travel across the continents. Towering tsunamis, hundreds of feet high, sweep over coastal regions, drowning cities, and reshaping the global coastlines. But the destruction is not limited to the oceans. The solid crust of the Earth, which we perceive as firm ground, begins to flex and bend. The tectonic plates are compressed and stretched by the tidal forces, generating friction and pressure. Globally, fault lines rupture simultaneously. Earthquakes of unprecedented magnitude shake the planet, destroying infrastructure, tearing down buildings, and splitting roads. According to the mathematics of tidal forces, the gravitational stretching is inversely proportional to the cube of the distance from the intruder. This means that as the massive object approaches Earth, the difference in gravitational pull between the near and far sides of our planet increases exponentially. This extreme stretching forces the Earth's crust to flex, releasing pent-up tectonic energy in a matter of hours, while the core itself is heated by the intense friction of the shifting mantle. The stress on the mantle activates magma chambers deep inside the Earth. Volcanoes that have been dormant for thousands of years erupt in a violent chain reaction, sending colossal clouds of ash and sulfur dioxide into the atmosphere. This dust shroud begins to circle the globe, blocking out sunlight and initiating a dark volcanic winter. As the Earth's core is distorted, our magnetic field begins to wobble and weaken, exposing the atmosphere to the harsh solar wind. The geodynamo at Earth's core, which normally generates our protective magnetic shield, is disrupted by the severe tidal pulling, causing our magnetosphere to warp. The planet's axial tilt, which determines our seasons, begins to swing out of balance. The geographic poles shift, causing rapid and extreme climate anomalies. Earth is now a planet in agony, its atmospheric and tectonic systems breaking down under the invisible grip of the cosmic intruder, struggling to retain its structural integrity as the gravity field intensifies. The planet trembles to its very core, entering a state of complete geodynamic breakdown as the orbital alignment changes, leaving no safe place left. The close encounter with the intruder reaches its climax. As the massive body swings past Earth, its strong gravitational field transfers orbital energy to our planet. In the language of orbital physics, Earth undergoes a gravitational slingshot. Instead of falling into the intruder or colliding with another world, Earth is accelerated to extreme speeds. Our orbital velocity increases rapidly, crossing the critical threshold of escape velocity. The gravitational grip of the Sun, which has held our world in place for over 4.5 billion years, is broken. Earth is ejected from the solar system. Our planet is now on a one-way path into the interstellar medium, heading out into the empty void. The consequences of this ejection are felt gradually but inexorably. The distance between Earth and the Sun begins to increase. In the dark sky, the Sun starts to shrink in size. Over the course of several months, the brilliant yellow disk that gave life to our planet transforms into a smaller, colder, and brighter star. The amount of solar radiation reaching our surface drops. Sunlight becomes weak and pale, similar to the light of a full moon on a clear night. This rapid decline in temperature is governed by the inverse square law of solar radiation. As the Earth's distance from the Sun doubles, the solar energy we receive drops to 1/4 of its original value. When we cross the outer boundaries of the solar system, the solar flux decay leaves our planet in a state of permanent energy starvation. The atmosphere begins to cool rapidly, and the warm winds that once drove our weather systems die out, replaced by a freezing stillness. We are completely isolated. As the Earth crosses the 5 astronomical unit threshold, the equivalent distance to Jupiter's orbit, the solar flux decreases to a fraction of its normal intensity. The final sunset on Earth is a slow, quiet event. The last rays of solar warmth fade from the atmosphere, reflecting off the glass windows of abandoned skyscrapers. The temperature drops rapidly. The sky turns into a perpetual night filled with stars that do not twinkle through a cooling, thinning atmosphere. The other planets of the solar system, also disrupted by the intruder, drift away in their own chaotic directions, separating from their ancient orbits forever. The solar system, once a structured system of worlds, is dismantled. Earth is now an independent rogue planet, a lonely vessel traveling through the cold vacuum of interstellar space, cast out from its cosmic cradle, moving toward the vast dark spaces of the galaxy where no sun will ever rise. We now wander alone in a silent cosmos, a frozen capsule of what once was a thriving world, drifting into the deep stellar graveyard of the Milky Way, lost to our home star forever. Earth is now a rogue planet, traveling through the interstellar medium. Without the sun's constant energy, the planet undergoes a rapid and total freeze. Within a few weeks of ejection, the global surface temperature drops to minus 100 degrees Celsius, and it keeps falling. The oceans are the first to change. A thick sheet of ice forms over the water, starting at the poles and quickly covering the equator. This ice sheet grows to a thickness of several miles, sealing the liquid water below it. The ocean becomes a dark, subglacial world, insulated from the vacuum of space by a barrier of ice. On the surface, the atmosphere begins to break down. As the temperature drops below minus 190 degrees Celsius, nitrogen and oxygen, the gases that make up our air, begin to condense. They rain down onto the frozen surface, first as a liquid, and then freeze into sheets of solid gas. The sky turns into a clear, empty vacuum, exposing the surface to cosmic rays and micrometeorites. The surface of Earth is now a dead, frozen wasteland, a dark museum of our past civilization. But deep below the ice, a remnant of life survives. The thick ice sheet acts as an insulator, keeping the deep ocean water liquid, warmed by the geothermal heat of Earth's core. This internal warmth is sustained by radiogenic heating, which is the thermal energy released by the slow decay of radioactive isotopes like uranium, thorium, and potassium in the Earth's mantle and core. Although the surface is locked in a frozen abyss, this internal radiator keeps the core hot, maintaining the liquid ocean beneath the ice for billions of years and providing a stable energy source for chemosynthetic life that does not depend on sunlight. This is our final shield. This core heating is driven by the decay of radioactive isotopes like uranium and thorium. Around volcanic vents on the ocean floor, simple ecosystems of chemosynthetic bacteria, tube worms, and deep-sea creatures continue to exist completely unaffected by the loss of the sun. For humanity, survival on the surface is impossible. Our only hope lies deep underground, inside massive bunkers carved into tectonic granite. These shelters are powered by nuclear fusion, using the heavy hydrogen in our frozen oceans as fuel. Inside these artificial worlds, hydroponic farms under ultraviolet lights grow crops, and recycling systems process water and air. Humanity becomes an underground species, living in a closed ecosystem powered by the internal heat of our dying planet. We wander the galaxy inside a giant rocky spaceship, a capsule of terrestrial life traveling through the cold void, waiting to see if we will ever pass near another star. We will survive in the deep underground shadows, carrying the flame of humanity into the eternal dark. But ejection into the cold void is not the only possible fate. The physics of gravitational encounters are highly sensitive to the initial alignment and speed of the bodies. If the intruder passes in front of Earth in its orbital path, it acts as a gravitational brake. Instead of accelerating our world, the encounter robs Earth of its orbital velocity. As Earth slows down, it can no longer maintain its stable distance from the sun. The balance between centrifugal force and solar gravity is broken. Earth is caught in a solar trap, falling inward toward the sun in a collapsing spiral path. The consequences of this fall are fast and violent. Over the course of several months, the sun grows larger in the sky, its heat and radiation rising to lethal levels. The oceans begin to boil. Millions of tons of water vapor are released into the sky, creating a thick, global blanket of clouds. This steam shroud traps the incoming heat, initiating a runaway greenhouse effect. The surface temperature rises rapidly, crossing the threshold of lead-melting heat. The continents dry up, turning into vast, scorched deserts before the rock itself begins to melt. As Earth falls inward, it eventually crosses the Roche limit, the boundary where the sun's tidal forces become stronger than the Earth's internal gravity. The planet can no longer hold itself together and begins to disintegrate. The crust is torn away in giant sheets of rock, which are vaporized in the solar corona. The extreme heat of the sun's outer atmosphere melts the remaining planetary core, absorbing the last traces of our world into the solar photosphere. This is the absolute and final end of our planetary journey, a silent vaporization in the solar furnace. The atmosphere becomes a heavy, toxic mixture of carbon dioxide and superheated steam. Earth transforms into a duplicate of Venus, a hellish world covered in sulfuric clouds and volcanic fissures. As the planet gets closer to the sun, the solar tidal forces become strong enough to deform the rocky crust. Giant cracks open and molten lava covers the surface. The planet eventually crosses the Roche limit, where the sun's tidal forces exceed the Earth's self-gravity, beginning to tear the planet apart. The final days of Earth are spent inside the corona, the outer atmosphere of the sun. The intense solar wind strips away the atmosphere, and the extreme heat vaporizes the rocky crust. In a final, silent flash, the remains of our world are absorbed by the sun's photosphere, leaving no trace of our history. Whether our fate is fire or ice, a gravitational encounter with a dark wanderer teaches us that our orbital position is a delicate privilege, a temporary sanctuary in a universe of moving monsters, where planetary systems are constantly reshaped by unseen forces. The potential paths of our planet, whether ejected into the frozen interstellar medium or pulled into the sun's furnace, force us to look at our place in the universe with a new perspective. We live on a world that has enjoyed stable climate and predictable orbits for billions of years. This long span of quiet time is what allowed life to emerge, adapt, and build a technological civilization capable of mapping the stars. But this orbital stability is not a permanent law of nature, but a rare, delicate privilege that we must cherish. We are currently traveling through a galactic shooting gallery surrounded by millions of silent, invisible monsters that roam the dark arms of the Milky Way. A rogue planet or a wandering black hole could cross our path, changing our history in a matter of months. Our current astronomical surveillance networks are blind to these dark objects until they are already inside our outer borders. We are, in a very real physical sense, living on borrowed time. Recognizing these threats is not a matter of panic, but of scientific understanding. The study of rogue worlds and stellar mass black holes helps us map the limits of gravity and stellar dynamics. To detect these silent interlopers before they breach our boundaries, we must expand our surveillance capabilities, deploying deep space telescopes that look for the subtle light warping of gravitational lensing. This astronomical challenge is a test of our technological resolve. We must keep watching the dark lanes of the galaxy, seeking to understand the movements of these wandering worlds. Because our survival depends on our ability to see the monsters in the dark before they see us. It teaches us to appreciate the rare stability of our solar system and motivates us to build better tools to scan the dark sky. Our tools, from ground-based arrays to space-based observatories, must evolve to peer into the shadows. If Earth were ejected into deep space, how long do you think humanity could survive using geothermal energy in underground cities? Share your calculations and thoughts in the comments below. Our journey as explorers of the signal is a continuous search for objective scientific truth in a vast, unpredictable universe that is constantly changing. As we look out into the dark, we must remember that the quiet orbital paths we enjoy today are the exception, not the rule. The silent void is a constant reminder of how precious our stable home is and how important it is to keep watching the sky. We must protect our home, using our scientific curiosity to map the movements of the invisible stars, because our future depends on our ability to see the threat before it is too late, ensuring that the light of human knowledge does not ever fade into the cosmic dark.